A dual-homed server appears simple. 2 links, 1 bond, 2 leaf switches. The control problem is not simple. Both leaves must describe one shared attachment, advertise compatible paths, elect exactly one designated forwarder for governed traffic, and present a stable LACP system to the host. The rejected assumption is that a healthy port channel proves evpn multi-homing. It does not. The core learning is this. Multi-homing works only when Ethernet segment identity, route types 1 and 4, redundancy mode, DF algorithm, and host-facing LACP identity form one consistent distributed contract. Here is our agenda. We shall define the Ethernet segment and its 10-octet ESI. We shall separate all active from single active service behavior. We shall use Type 4 to discover peers and Type 1 to advertise attachment reachability. We shall examine default, HRW, and preference-based DF election, including service carving and capability agreement. Then we shall connect the evpn control plane to the host-facing LACP system identity. Finally, we shall build a verification chain, from local configuration through received routes to one unanimous DF result. The objective is coordinated state, not 2 independent access links. An Ethernet segment is the set of links connecting a customer device or network to one or more PEs. evpn names that shared attachment with an ESI. The 2 leaf switches may use different local interface names, but they must advertise the same non-zero ESI for the same segment. A different physical attachment must not reuse it anywhere in the evpn domain. Remote PEs use the ESI to recognize multiple advertisements as paths to one attachment, rather than a MAC move. Therefore, the allocation system must validate the complete ESI across the fabric, not merely a local numeric suffix. The ESI is a 10-octet value. 0 means a single-homed site, and the all ones value is reserved. Type 0 allows an operator-managed value. Other types derive bytes from identifiers such as an LACP system MAC and key, or a system MAC with a local discriminator. Derivation algorithms differ among implementations, so identical configuration labels do not guarantee identical ESI bytes. For interoperability, record the rendered 10 octets, the type, derivation inputs, and the Ethernet segment owner. Verify both PEs advertise the same value and scan the full fabric for collisions before enabling the attachment. In all active mode, eligible PEs may forward known unicast to and from the customer attachment, and the customer commonly hashes flows over one LACP bundle. The DF alone sends overlay-originated BUM traffic toward the segment for a service. In single active mode, only the DF forwards the governed unicast and BUM traffic. Remote alternatives remain backup paths. These are service semantics, not cosmetic configuration. A peer mismatch can create duplicates or black holes. Confirm the mode in the Type 1 ESI label community and in local forwarding state, and verify that the chosen implementation actually supports the requested mode. Each PE attached to the Ethernet segment originates a Type 4 Ethernet segment route containing the ESI and an originating router, IP. An ES import route target scopes reception to the other PEs attached to that segment. Optional DF election communities advertise algorithm and capability information. After import, every participant should see the same set of candidate router IPs and compatible election parameters. Type 4 does not advertise tenant MACs or service reachability. It establishes who participates. If one PE misses a Type 4 route, the two sides can elect different DFs, even while ordinary evpn routes appear healthy. Type 1. Ethernet auto-discovery routes describe paths through the shared attachment. The per Ethernet segment form has broad scope and enables mass withdrawal. Removing one PE from the segment can invalidate many dependent MAC paths without waiting for individual Type 2 withdrawals. The per EVI form states that a PE participates in a specific service on that ES and is used for aliasing or backup path procedures. Support and defaults for EAD per EVI differ across implementations. Therefore, a common profile must explicitly decide whether it is transmitted and required, and packet tests must prove the resulting remote path set. The original DF algorithm orders candidate PE router addresses and uses the Ethernet tag modulo the number of candidates to select one. Because the result is per Ethernet tag, different services can be carved across the PEs. The algorithm is deterministic when every participant has the same candidate list and input value. Its weakness is disruption. When the number of candidates changes, many services may move, even though their former DF is still healthy. This is why DF state must be checked per ES and service, not merely as one chassis-wide role, and why newer algorithms were standardized. Highest random weight, or HRW, computes a weight from the Ethernet segment, service, and each candidate, PE. The highest result wins. When a candidate leaves, services assigned to surviving DFs normally stay in place, while only the failed candidate's services move. RFC 8584 also defines a DF election finite state machine and signaling so peers can agree on supported behavior. If participants advertise different algorithms, fallback and compatibility rules matter. Never assume that enabling HRW locally makes the segment use it. Inspect the received DF election community and the operational algorithm on every PE. Preference-based election adds a direct administrative signal. Current RFC 9785 defines highest and lowest preference algorithms, a default preference, tie-breaking, and an optional do not preempt behavior. This is useful when one leaf should be preferred because of capacity, locality, or maintenance intent. It also creates an interop risk. Older software and design documents may support a draft version, one preference mode, or no standard fallback. Treat the algorithm number, preference range, tie-break, and preemption mode as negotiated profile fields. Test equal preference, unequal preference, failure, recovery, and mixed capability rejection before deployment. A PE may remain alive advertise type 4, and reach the evpn core while one local VLAN or attachment circuit has failed. If election ignores that service-specific failure, the PE can remain DF for BUM traffic it cannot deliver. RFC 8584 defines attachment circuit influence capability to address this class of problem. Implementations vary. The operational invariant is simpler than the mechanism. The elected DF for a service must have a usable local attachment, and all non-DFs must enforce the intended filter. Test a member link failure, whole bond failure, and one VLAN failure separately. They do not produce the same control inputs. In an all-active LACP attachment, both leaf switches must present a compatible actor system identity, so the host forms one bond rather than two unrelated aggregators. The LACP system, MAC, system priority, and key must align with the host's expectations. That identity is not the same thing as the ESI, although an implementation may derive one from it. It is also not the VTEP address, chassis MAC, Anycast gateway MAC, or evpn routers MAC. Record every identity separately. Verify the host sees one aggregator with all expected members before interpreting any evpn route as a working multi-homed service. Multi-homing configuration must be validated as a pair. Different ESs make one attachment appear as two sites and can trigger false MAC mobility. A different ES import, RT, or missing type 4 route creates divergent peer sets. A DF algorithm or preference mismatch can produce inconsistent winners. An EAD per EVI mismatch can suppress remote alias paths. A different VLAN to VNI set makes only some services fail. Configuration generation should compare both PEs before deployment and fail closed. Runtime monitoring should alarm on candidate set, algorithm, mode, and service membership disagreement, not only on BGP session loss. Use one evidence chain for each Ethernet segment. Compare the complete rendered ESI and local mode on both PEs. Inspect locally originated and received Type 4 routes, including ES import RT and DF election community. Confirm the candidate list and algorithm are identical. Inspect per ES and per EVI Type 1 routes and the remote path set they create. For several Ethernet tags, compare the DF and non-DF result on every participant. Exactly one winner must exist for governed traffic. Finally, verify the host bond and send known unicast and BUM test traffic. Route agreement without correct filters is incomplete. The core learning is this. evpn multi-homing coordinates multiple PEs by naming one shared Ethernet segment and distributing explicit reachability and forwarding roles. The ESI correlates the attachment. Type 4 discovers candidates and carries election capability. Type 1 supplies segment and service-scoped paths. The redundancy mode defines whether alternatives are active or backup. DF election chooses one permitted egress for governed traffic per service. LACP presents one coherent system to the host. Prove every link in that chain on both PEs. Do not trust a port channel, a route, or a DF flag in isolation. Demand unanimous control state and representative packets.